Almost every RF signal in nature starts as a sinusoidal waveform. Whether it is a carrier wave, an antenna signal, or an oscillation in a circuit, sine waves are the fundamental building block. In this lesson, we will understand sinusoidal functions and why they are the natural language of RF signals. Sinusoidal functions are the most important signal shape in RF engineering because they naturally describe oscillatory behavior in physical systems. Whenever energy is exchanged between electric and magnetic fields, or whenever waves propagate through space, the resulting signals tend to follow sinusoidal patterns. This happens because sinusoidal functions are solutions to many fundamental differential equations in physics, especially those involving harmonic motion and wave propagation. In electrical systems, inductors and capacitors naturally produce sinusoidal responses when excited by energy inputs, making sine waves the natural steady-state behavior of many circuits. Because of this, RF engineering treats sinusoidal functions as the fundamental building block of all more complex signals. A sinusoidal function is defined by three key parameters: amplitude, frequency, and phase. Amplitude represents the strength of the signal, frequency determines how fast it oscillates, and phase describes its position relative to a reference point in time. These three parameters fully define a sinusoidal signal, making it one of the simplest yet most powerful representations in engineering. Despite its simplicity, a sine wave can describe a wide range of physical phenomena, from electrical oscillations to electromagnetic wave propagation. In RF systems, these parameters are constantly analyzed, modified, and transmitted, making sinusoidal functions a central tool in signal design and communication. In the time domain, a sinusoidal function represents a smooth and continuous oscillation that repeats itself over time. This repetition is what makes it ideal for representing periodic signals in RF systems. When plotted over time, a sine wave shows alternating positive and negative values, representing the oscillation of voltage or current in an electrical system. This oscillation is not random, but follows a precise mathematical pattern determined by its frequency and phase. Understanding sinusoidal behavior in the time domain is essential for analyzing how signals evolve and interact in real circuits. One of the most important properties of sinusoidal functions is that they can combine with each other in predictable ways. When two sine waves interact, their resulting signal depends on their relative amplitude, frequency, and phase difference. If two sinusoidal signals have the same frequency but different phases, they can either reinforce each other or cancel each other partially. This behavior is fundamental in RF systems where interference, modulation, and signal mixing occur. Because of this predictable structure, sinusoidal functions are extremely useful for analyzing complex signal interactions in communication systems. In RF engineering, sinusoidal functions are used to represent carrier signals, modulated waveforms, and electromagnetic wave propagation. Almost every wireless communication system relies on sinusoidal carriers to transmit information efficiently over distance. Antennas radiate sinusoidal electromagnetic waves, while receivers detect and process them using frequency-selective circuits. Even complex modulated signals are ultimately built from combinations of sinusoidal components. Understanding sinusoidal functions is therefore essential before moving into more advanced topics such as Fourier analysis, where complex signals are decomposed into sums of sine waves. In this lesson, we learned that sinusoidal functions are the fundamental building blocks of RF signals. They describe oscillations in time using amplitude, frequency, and phase, and form the basis of all wave behavior in electrical systems. In the next lesson, we will explore vector basics and understand how RF signals can also be represented geometrically. If you found this useful, like the video, subscribe, and follow for the next lesson.